Perfect. Thank you all for being here today for our last session of the fall 2024 edition. And today we have the pleasure to have here with us Lydéric Bocquet, who's a professor at CNRS and École Normale Supérieure de Paris. And Lydéric is going to talk about the molecular mechanics of fluids. So first of all, Lydéric, thank you so much for being here with us today and for having accepted to present your work and to give a class as part of our webinar series. And you can start sharing your presentation. And Leah, let me know if you can see Lydéric's presentation.
Perfect. I can see it.
Perfect.
Okay.
I'm going to stop mine. Okay. So people, you know how it works. If you do have questions, it's very okay for Lydéric to answer them during the talk. So raise your hand, write the questions in the chat, do whatever you want. It's better if you talk loud to have a discussion. Anyway, let's enjoy Lydéric's work and class, please.
Okay, so thanks a lot, Michel, and thanks, Leah, as well. So I'm really glad to speak today about this work. So actually, my presentation will be divided in two. So one part of it is more kind of a general introduction of what I call the molecular mechanics of fluids. So basically, fluidics at the nanoscales. And in the second part, I will go more deeper into one question, which is of interest to me for a long while. So I'll be discussing these more specific questions. So actually, oops, if I can. Okay, so I've been working in fluids for, I don't know how many years. And what I found always amazing, for me, is this beautiful equation, the Navier-Stokes equations that you all know, I guess, in this audience. And what strikes me is that you have a single equation, and with this single equation where you have only one single parameter, which is the viscosity here. Okay, I consider the incompressible equation. You can really describe nature at huge, in a huge, broad range of length scales. From microbes to hurricanes and even larger, let's say, galaxy and waves. And this is stone skipping because that was the topics on which I worked some time ago. And so what I found really incredible is that you have a single equation, and this is able to have such a huge richness of applications. And let's say the DNA of the fluid is all hidden in the viscosity. All the molecular details are hidden there. So it's incredibly robust and amazingly efficient. And at the same time, it's completely universal. But okay, of course, as a scientist, you always want to push the boundaries. So find systems where this kind of equation is not relevant anymore. And that's why I guess like many of you have been interested some time ago or so to complex fluids, so granular system, foams, gels, and etc. Because there, indeed, you break the universality of Navier-Stokes. You have to reinvent a new constitutive law. And what I've been looking at that time with collaborators is confinement effects, actually, of flows. And in particular, I was interested in granular system, but also soft glassy flows, where we showed the occurrence of non-locality in these systems, and where we had to go beyond the simple idea of viscosity, and we introduced the idea of fluidity and non-local fluidity, and etc. So that was one way to, let's say, to push the boundaries of Navier-Stokes. But then, okay, going further, then at some point I turned to the limits of let's say flows whenever they are confined into extremely small confinement. So let's say, can you, for example, I show you here a movie of water molecule flowing in a carbon nanotube. So that's the molecular dynamic simulations. And you can ask, is the Navier-Stokes equation valid there? And can you do you expect some deviation and etc. And what can you expect? And actually, this point to me connects to something which always amazed me, is the incredible richness of nature. When you look at nature in our body, but in plants, and you have lot of pores and channels which are a few angstroms in thickness, and some of them. So I show here the movie of an aquaporine. So that's a filter of water which is super efficient and super selective. But then you have more advanced systems like ionic pumps and all active channels, which can, for example, pumps can really transport ions or other solutes against the gradients. So it's an active, it's a really a machine, a small machines. And then you have all these mechanosensitive, which I will not discuss. And you see that in all these systems, first you have very strong confinement down to the molecular scales. And I think this is interesting because in some sense, if you want to break the universality of Navier-Stokes, you need to go down to the molecular scales. And beyond this universality, you can have a lot of new behavior. And that's what is, I think, interesting. And so I will, of course, not comment, but I just put here random papers in the literature is that it's interesting that you in nanochannels and this field of nanofluidics, let's say the study of flows at nanoscales, in some sense really emerged, let's say 10 to 15 years ago, where people were started to be able to fabricate systems, so nanopores at the nanoscales, and really measure things. So I just make a random collection here of example. And so I will just give you just a few examples, and it will not be exhaustive, but just a kind of an overview of what could be done. So what I found first interesting is all the the appearance of a new thermodynamic phases, new thermodynamic behavior whenever you confine a fluid in very strong systems. For example, there were all the work by Michael Strano and his team, etc., about the phases of water inside carbon nanotubes. So they did Raman studies of these systems, and they really showed that, for example, water can crystallize at room temperature in these systems. Then there were some studies in 2D systems, and I will come back to how to fabricate these systems in the group of GAIM, where they said, oh, we may have some square lattice of water inside a very strong confinement. So it was really a molecular confinement. Actually, so this paper was debated because some people didn't believe it was water, but that's a TEM flow. Then I just show this, for example, that's a simulation here using ab initio simulations, so quantum simulations plus machine learning. So that's the hype lately, but that's really important in this field to boost the simulation. And in these systems, they show that in very strongly confined system, water can go in various phases, but one phase which is extremely interesting is what is called the superionic phase, where basically the water molecules comes into parts, and basically you have only ions, and this is a superconducting phase, a bit like a superconductor, but for ions. And that would be extremely interesting to have these systems under mild conditions. Then, okay, here I show capillary condensation, so maybe I will skip this part. But the point in all that is that, okay, when you go to channels where you have I just here take a picture, you have just a few molecules in width, can you still apply the continuum? So that was the starting point. And when does the continuum break down? And actually, so this is a question which struck me for a long while. And I think, of course, when you go down to the molecular scale, of course, you expect Navier-Stokes to break down. It's a continuum equations. Actually, an interesting way to see is that Navier-Stokes equation can be valid if basically you separate the molecular scales to the long hydrodynamic scales. So it's a time scale separation which is at play. And then for the micro scales, typically it's a picosecond for water at room temperature, and this is it's the typical molecular times which you can build in terms of the mass, diameter of water, and the typical energy of interaction. Now, hydrodynamic time scale is a diffusion of momentum. So it's a length square divided by the kinetic viscosity. So basically, when you say this has to be smaller than this hydroline scale, then you get a length scale, which is the square root of the kinematic viscosity times the microscopic time. It's typically 1 nanometer. And actually, this the boundary of 1 nanometer does really work in reality. So you see that above 1 nanometer, basically you can apply the Navier-Stokes equation. And this is inferred by experiments, but also simulation and etc. etc. So this you should keep this in mind. So that's a good news because it means that the Navier-Stokes equation is valid down to very strong confinement. But it's a bad news because if you want to see deviation, okay, you may have to go below 1 nanometer in confinement. That's very harsh to fabricate. But remember that all the biological systems works below the nanometer actually. So that's interesting that then you have the non-universality of the Navier-Stokes. Then of course you have the hydrodynamic continuum, but you have in plenty of other continuum. And one key aspect is, for example, what I would call the dielectric continuum. So because you apply, for example, electrostatics, where ions interact to each other. And there were some very beautiful experiments by Laura Fumagalli in the group of Manchester, so close to Gaim, and where they really measured, they could measure the dielectric constant of super confined channels. And first they measured what is called the out of plane, so the perpendicular dielectric constant, because now it becomes a tensor. You have a perpendicular dielectric constant and a parallel one. And actually, what they showed, and it was a paper a few years back, that the dielectric constant starts from the bulk value of 80, but decrease as you see the channel thickness decrease. And it goes down to basically 2, a very small value in very strong confinement. But actually, okay, that was interesting, and that's very interesting actually. But the point is that this is merely a surface effect. That it in the end, it says that you have a bulk center, and actually close to the surface, the dielectric constant within a few angstrom is much smaller, and this you expect in terms of polarizability of water. That was interesting. But lately, I mean, they did another set of experiments. So this is on archive. Against by Laura Fumagalli and her team. And whereas now they are able to compute the lateral dielectric constant. So that was the previous one I showed. Here's the lateral. And here the behavior is very different. So you see, you have down to a few nanometers, basically the bulk water, and then a sudden jump here at small confinement around 2 to 3 nanometers, whereas the dielectric constant goes up to 1000. Which is a bit strange, and also they measure the in-plane conductivity, but which I will not comment, but you also have an anomaly around a few nanometers. So how to understand that? I mean, that's completely open. And there are a lot of simulations, and they are not able to recover this data. So that's typically the kind of effects that you are able to measure in this super confined system. And actually, when you look in all the length scales, and actually, the interesting part of nanoscales is that you have so many phenomena which are enter into the game. So, and I previously discussed continuum versus molecular scale. So that's 1 nanometer. But actually, you have plenty of other scales which enter the game. And I will not discuss them one by one. I mean, I made that in some reviews. But you have, of course, electrostatics, friction. I will discuss friction later, fluctuation, dielectric anomalies I was saying, also quantum effect, which I will discuss shortly after. And actually, what in this domain, what we have in mind is that actually when you go below 10 nanometer in size, which my American friends say it's a single-digit nanopore, so that's a fancy name to say it's below 10 nanometer. And there you have a lot of strange things which occur. And that's the interesting part of it. So, I mean, now, okay, I told you that, okay, nanofluidics emerged, let's say, 10 years, 15 years ago, something like that. Actually, what triggered the emergence of this field is really the ability of fabricating nanochannels with very precise confinement. Of course, I mean, nanofluidics occurs in porous media and membranes and everywhere. I mean, so that's a very, in some sense, all the phenomena that I discussed, we know that they should occur also in all these porous macro scale systems. But here, the interesting part is that we were able to fabricate systems. And so, okay, the point is that when you do a simulation, molecular simulation, let's say it's quite easy because you put molecules, you put interaction between water, more or less complex. Maybe you go to ab initio if you want to do some quantum simulations. But okay, that's quite easy. But now, the point where we were in 2010 is how do you make that in a real system? And we were really helped by all the progress that were made in nano devices and all in condensed matter, let's say. And of course, there were all the developments of carbon nanotubes, of course, some time ago. Also, boron nitride nanotubes. So we discussed shortly boron nitride. It's interesting. Boron and nitride are the neighbors of carbon in the Mendeleev table. And you can fabricate nanotubes which have exactly the same structure, crystallographic structure as carbon, but carbon is metallic while let's say close to metallic, and boron nitride actually is fully insulating. So that's very interesting to compare the two. And there are all the 2D systems which are made with van der Waals assembly, and I will tell you a bit more about that. So just how we do fabricate, for example, a system where you want to measure something current inside or flow inside a single nanotube. So what we did, it was really brute force. So we did this 10 years ago. So we used basically nano manipulations. And this is what you see is a carbon nanotubes at the end of a tungsten tip. And under the SEM, you introduce the nanotube inside the hole, and you are able to glue it, actually. So it was really a nano fabricating system. So here previously it was, oops, so maybe I should show again here. Previously, it was in the hole of a membrane, which you inserted nanotubes. Here, it's inside the hole of a nanopipette. So it's a Pasteur pipette, which you pull, and you can indeed insert a nanotube at the end and glue it. And so actually, over the years, we really learned how to fabricate these systems, cut the nanotube, glue them, and etc. And sorry. And at the end of the day, so oops, okay. Okay, so the movie, okay. And at the end of the day, okay, you put, for example, water inside the system. So here it's like a fluorescent system, and you have a nanotube somewhere here, and you are able to explore the flow across the system. So measuring things, it's okay. Once you have the nanotube inside the membrane, you have basically you can put two reservoirs on both sides, as I show here. And for example, put electrodes and put a difference of voltage and measure the current. And measuring currents is quite easy because actually we benefit from the work of people doing physiology for so many years, where people are doing single ionic channels measurements for more than 50 years now. So it's easy to measure currents, and so that's what we did a lot. For example, current across tiny nanotubes. For example, here it was measurements. I just show an example, and I will discuss more in details later. But this was a measurement across the systems with a size around 2 nanometer in radius. And there, for example, just to show you that we could apply here both voltage drop, where you measure conductance, and pressure drop. And you can combine the two. And we found, for example, in these systems that you have a nonlinear response, where the conductance, in this case, depends on the pressure. So that's something which is really unexpected, and a combination between mechanical work and electrical response. And okay, so I will not discuss this work, but it's just to highlight that indeed we can measure things there. Now, a big advance, a big progress was made a few years back, actually, in the group of André Geim. So you know, it's a Nobel Prize for graphene. And actually, it was a great idea that they had, is to, you know, in these systems, you can do assembly of various systems. So let's say graphite, and you can deposit graphene, and you can deposit on top of graphene another graphite. And actually, what is interesting is that the graphene, as it's shown here on the top, you can actually mill, you know, some stripes. So you have here a spacer made of graphene, which is just a few layers thick. And you can really control the layer of graphene from multi-layer graphene in the range of tens of nanometer down to one single layer, and one single layer is 3 angstrom. So you can really, with this technique, you can fabricate channels with a size which goes down to a few angstrom. So that was a great success and of the group of Geim, and so this is called van der Waals assembly, because basically you glue system on top of each other just by van der Waals forces. And you are able to do this kind of channels where the thickness here is just a few angstrom. So that's a great systems. And actually, in my team, we learn from them how to fabricate these kind of systems. So that's very, no, we do it. Okay, you need a clean room, but actually you can do it every day. And with this system, actually, also you can measure things. And yeah, just show a few examples. For example, you can measure the conductance, of course, across these systems, which are down to few angstroms. For those who know zeta potential, you can measure electroosmotic mobility. For example, in this system, you apply a pressure drop and you measure current, an electrical current. So this allows to measure the zeta potential. So you see, in these systems, and again, it's just an overview for now. I will come back to physics a bit later. You can get, with this system, you have a lot of insights about the physical chemistry in a very controlled way. And for example, in these systems, we could infer that you had on graphite systems, which is a perfectly clean surface of graphite, you may have adsorption of OH minus, physisorption of OH minus, while on HBN, so the boron nitride, you have a chemisorption. So you start to have very a lot of detail about the chemistry at this interface. Actually, you can do much more because it's a 2D system, of course, because basically in this system, you only have, for the strongest confinement, you have only a single layer of water. And there you have really 2D systems, and you know that in 2D things are a bit weird. So you can study a lot of 2D physics there in this experimental system. So, okay, we worked on many aspects of that, and we have been playing with these systems for a long while. But what I think what I wanted to say in this first part is to say that what is interesting is that it was worth the effort of doing all this system, because what emerged in this field that there are a lot of strange behavior, and you know, as physicists we always love to see strange things occurring. And for example, I will come back to that you have, for example, the flow across nanotubes is super fast, so incredibly fast. You have a lot of non-linearities in ionic transport. And you have analogies with what is called the electronic Coulomb blockade. You have the same with ions. A lot of neuromorphic effects that we play with this system to do a kind of a bit of learning. So as if our 2D systems were behaving like a bit like neurons, which was, and a strong part of what we discovered later is that we start to see quantum effects, and when you confine to this, and this I will discuss more in details. And okay, so in this first part, I was trying to give you this kind of overview of what we can do, what we can fabricate, what we can measure. And now I will go more into one question, which was interesting to me for a long while, and actually it was basically quite a journey and quite an adventure, as you will see. And actually, it happens that for 20 years, there's been a lot of measurements of flow of water across membranes made of carbon nanotubes. And the first ones were done in 2005 by the team of Backaging and others. What they found is that the permeability of this membrane, so made of many nanotubes in parallel, so billions of nanotubes in parallel, the permeability was much higher. I mean, you see here, this is a flow enhancement versus a nanotube diameter. So the permeability of this membrane was much higher than what you expect with Navier-Stokes equation and a no-slip boundary condition. So this flow enhancement actually is the result of what you expect if the friction of water on the surface is much lower. I mean, the friction is not infinite, the friction is finite, and this is the slip length, and I will come back to this definition. And this enhancement tells you that the permeability is much higher. You see up to 4 orders of magnitude. And this seems to depend on the diameter. Okay, first you see that you have a lot of dispersion. So it's basically astrophysics scales because you have a log scale on both sides. And honestly, this remains a mystery actually for 20 years. And this motivated us actually a few years back to do measurement with single nanotube. And this is what I would like to discuss now. So Okay, now let's put a few definitions. Actually, it connects to the talk and the class by Frédéric Restagnol, where he discussed a bit of slippage, notably in polymers. And here you have the same, that if water flows against the surface or inside a nanotube, of course, it will have some friction on the surface. And actually, this goes to what is called the Navier boundary conditions, where instead of having no slip, where the velocity is zero at the surface, you may have a finite velocity at the surface. And to quantify that, we introduce a slip length, B, which is an extrapolation length, as on this graph here. So you extrapolate, and the flow would vanish at a distance B from the surface. But actually, physically, the key quantity is the friction coefficient here, which relates the force per unit surface to the slip velocity. And it's easy to show that the slip length is simply the bulk viscosity divided by the friction coefficient. So the friction coefficient is really the physical parameters, and the slip length is just a simple way to present that. And so I've been working on these topics for a long while, and basically for most surfaces, the slip length is zero, actually within nanometer. For if you look at the water on a glass surface, it will be zero slip length. But if you go to carbon nanotubes, I mean, to account for the results which I showed you before, I mean, this result here, you need a slip length which is in the range of I mean, hundreds to thousands of nanometers, so much, much larger. So it's really an anomaly that carbon has. And on top of that, the slip lengths, the value for the slip lengths at large radius do not match what happens at small radius. So there is something strange there to understand. So water and carbon is an odd couple, and we wanted to understand why it's an odd couple. And so a few years back, we developed this experiment to study the flow inside a single nanotube. So the study there followed what I showed you before. So first, we fabricated a system where we put a Pasteur pipette, and at the end of the Pasteur pipette, we could put a single nanotube. And we can glue this nanotube in the Pasteur pipette. And then we put this Pasteur pipette in a big reservoir, and we put water in the Pasteur pipette, and we put some pressure on the fluid here. So then what you expect here is to create a water flow across the nanotube, and this will create a nanojet in some sense. And of course, this nanojet, the flow of water across this nanojet is extremely small, because you can imagine, I mean, there are just a few water molecules which across the carbon nanotubes per second. So that's a very tiny flux. So it's basically impossible to measure the flux. But it happens that with this setup, we could measure the force which is induced by this nanojet. And that's a bit like, you know, in the fall when you have this blower in the streets where you make some wind out of the blower and you push the leaves. So, and from the velocity of the leaves, actually, you could infer the flow across the blower. So that's exactly the same. So we did put some colloids inside the reservoir, and these colloids are blown away by the flow across the nanojet. And so that's exactly what is shown here. So at the bottom, so you see that's really an experimental picture. So you don't see the nanotube. Okay, the pipette is sketched here. And you see you have these trajectories. That's the trajectories of the colloids which are pushed by the flowing across the nanotube. And what is impressive, actually, you see that this flow occurs over tens of microns. So that was because then it's measurable. It's an optical measurement. And actually, this flow, you can find its solution in the Landau book of fluid mechanics. It's called the Landau square jet. It's one of the few analytical results you can find for the nonlinear Navier-Stokes equation, actually. And so here it happens, it's fully linear, but actually you have an exact solution for the flow. It's a Stokeslet, basically. So it's really the fundamental of fluid dynamics. And from this flow, you can infer what is a momentum transfer, so how much of velocity comes out of the nanotube. So if you know the velocity of water, you can infer the flux. So you can measure the flux for a given pressure. So from the flux, you can extract the permeability. And if you have the permeability, you can extract whether is the permeability equal to what you expect for the Navier-Stokes with no slip, or do you obtain something else? And actually, what we measure exactly is the slip length. From what I told you before, the slip length actually accounts for the enhancement over what you would expect with no slip. And so these are the results that we got from these experiments. So first, I show you there are two types of systems, so the carbon nanotubes and the boron nitride nanotubes. And as you could see, for the boron nitride nanotubes, it was interesting because the flow was exactly the flow given by Navier-Stokes plus no slip. While for the carbon, the slip length is quite large, so hundreds of nanometers, meaning that the permeability is a few orders of magnitude larger as compared to what you would obtain with the no slip boundary condition. I should have shown you the permeability. I'm sorry for that. I forgot to show it here. And the second point, which is, so first, you have a huge difference between the carbon and the boron nitride, which is a first strange thing. The second point is that the slip length with carbon increases when you decrease the tube radius. And it increases, you see, around 20, 30 nanometers. And that's really, really strange to understand. So if you plot instead of the slip length, you plot the friction coefficient. So that's really the friction of water on the surface. Actually, the friction for water on the carbon decrease with the radius. And I have to say that these experiments were done with multi-wall nanotubes. So actually, you have a large number of layers of carbon, and that was a constraint for our experiments, because if you have only a single wall nanotube, it's too slopey, and you cannot put it at the end of the tip. But then you see, that's very strange because HOPG is flat. So that's basically the limit of an infinite radius. And so you have HOPG, and there you see the friction decrease. Okay, it does not go to zero. We would have loved that this goes to zero because it's basically like superconductivity, but no. So the friction goes to a very small value, but non-vanishing, and decrease with the radius. And actually, HOPG is graphite, so multi-layer graphene, let's say. And actually, there were some measurements on graphene, very few actually, and it's difficult actually these measurements to be done. And actually, graphene actually is there is a bottom value which is also the value of friction on graphene is very small as compared to graphite. So it's another thing which is difficult to understand in these systems. So you see, all this is very unusual and unexpected. And so you see, we tried to solve a mystery, and we went into another mystery because okay, now we have this to understand. But at least we were happy because we had, in some sense, constrained data, and on a single nanotube allows us to control everything, more or less. Okay, now the point is, how do you understand that? And it's really a question of friction of water. So okay, so in Navier-Stokes, basically you have, let's say, fluids on a wall. The wall is basically is just described by a velocity equals zero on the wall. Of course, if you do molecular dynamic simulations, okay, you have maybe this kind of configuration with water molecules, and the wall is here, it's a carbon nanotube, and maybe the carbon can jiggle a bit, but not so much. And we come back to this question of slippage. So what is the slippage of water on these fluids? Or what is the friction of this? And to make a long story short, there have been a lot of simulation on such systems, molecular dynamic simulations, which describe water with various models of water and how do they exhibit friction on the carbon systems. And a long story short is that the friction in these systems were, I mean, this molecular dynamic simulation were unable to explain this data, this experimental data that we had. And so that was a great mystery. And so then that's why we, at some point, we turned to one of the missing ingredients on all that is the internal degrees of freedom of the wall. And in particular, graphite contains electrons, of course. It's a conductor. Okay, the nanotubes can be conductors, semiconducting, etc., but at least you have electrons. And the question there is that if water has some charges, so whenever it will flow on the top of the graphite, of course, you have a kind of a sea of electrons, and this charge will move across the sea electrons, so it will move the electrons in some sense. And so we were wondering whether this movement of the electrons could be sufficient to induce a friction, a supplementary dissipation, so the internal degrees of freedom. That was a bit, in some sense, desperate, because when you think that the electrons have a very small mass, so as compared to the water, so usually, I mean, you cannot. It's a bit like flies around a cow, so you cannot break a cow by some flies. So that was a question, and so that's what we tried in particular with Nikita. He was PhD, now he's at EPFL, and Marie-Laure Bocquet, my wife. And actually, so just I will just introduce one quantity, and I will not enter into the too much of details of the physics. But I think what important quantity, of course, an electron gas, actually, what is important here is that it's described by its dielectric constant. So, and the dielectric constant, okay, you know that it's 80 for bulk water in the static mode, so for low, small frequencies. And but actually, in general, it depends on the wave vector and the frequency. It's a bit like a mechanical response. It depends on the Q and omega. Actually, it happens that for the calculation, I introduce another quantity which is basically contains the same information as the dielectric constant, but it's particularly suited for semi-infinite systems. So let's say that's it's basically the integral of the electronic response over the system. Actually, okay, this is basically the spectrum of electrons. So if the electrons are described by an harmonic oscillator, this would contain a peak at the harmonic oscillator frequency. So that's basically what you should get into it. Actually, it happens, and that's a fun fact that this surface response function, first, it can be measured by some experiments. These experiments are called Eales experiments. And second, is that in some limits, is that the response function is exactly the reflection coefficient of in optics, like in Maxwell equations. So that's so basically what I'm discussing here is can all be discussed in terms of reflection of waves, electromagnetic waves on the surface. And this is basically what I mean. There was this very beautiful paper by Pendry in '97, and which I mean, he has various descriptions, but one description is optical. You can describe all these by optics, of course, because it's fully analogous. So, okay, I will not discuss. I just put the formula so that you have the formula, but I will just show you the physics contained in all that. So, what we did actually is to calculate, and actually that's what Nikita did in his PhD. Put the whole water, so the water fluctuates, and you have electron. An electron fluctuates, and they interact via a Coulomb potential. And at the end of the day, you have two types of friction. A friction which is due to corrugation. So, for example, water will flow on the corrugation of graphite, for example. It happens that for graphite, it's very small because graphite is very, very flat. But then you have a second contribution, which is called the quantum friction, actually. And this friction comes from the fact that if water moves, it has some charge fluctuation, and this charge fluctuation may couple to the charge fluctuation of the electron. And if they are able to talk to each other, you have friction. So that's why, I mean, in this formula, forget about all the details, but the key point is that the friction coefficient is proportional to the overlap of the electronic excitation and the water excitation. It's a bit like if you have two oscillators, if they have the same frequency, they get in resonance, and then you have a lot of dissipation, a lot of energy which can be transferred from one to the other. So now what are these spectrum of excitation? It happens for water, it's extremely well known. Water, when you go to the molecular scale, water is actually it fluctuates. There are a lot of charge fluctuation, and it happens that the charge fluctuation has the shape of a big peak, which is called the Debye peak, around gigahertz, but up to terahertz. Actually, this peak is what you use when you put your things in microwave. You excite water, and then you see actually exciting at the frequency close to frequency. The resonant frequency give you a lot of warming. So you transfer energy actually, and so that's a big peak. It's called the Debye peak. You see it's very broad in terms of energy and frequency. And actually, the Debye peak is really the collective fluctuation of water. Actually, so here I show you the this spectrum of water versus frequency. You can show it frequency and wave vector. So you see it's basically flat. So in terms of wave, it's a flat wave, basically, more or less. Now, okay, electrons. Okay, electrons, I will not do condensed matter class, but the point is that electrons also have waves. And one wave you may have heard of is, for example, plasmons. Plasmon is charged waves on the surface here. And so basically, that if you excite the system at the charge system at the surface, it will propagate charge waves. So that's a surface plasmon. In terms of energy momentum, you have, for example, this kind of dependence, etc. So the question now, do this excitation talk to these electronic excitations? So, okay, so now, okay, of course, the first thing you want to do is to look at graphene, because graphene, that's a nice 2D systems, and everything can be done analytically, and you find this in a textbook. So in the textbook, basically, you find that the energy versus momentum, you have a surface plasmon of graphene. So you see graphene is a 2D layer of carbon, graphite, and you have waves of electrons moving in this direction. But you see that the overlap between these yellow parts of water, this water excitation, and this, you see here the energy in the range of a few millielectron volts, tens of millielectron volts. So it would basically these two systems here would be around here. And you see that you have barely any overlap. So you expect that in this formula, the overlap between graphene and water is basically zero. So you have no quantum friction for water on graphene. No, and that was actually, I think that's the most interesting part and the big surprise. It happens that graphite, so graphite, remember, it's a succession of graphene. So graphite is like that. So you see, you have a lot of graphene layers. While graphene, you have a single layer, and graphite, you have many layers on top of each other. And so actually, on graphite, it happens that it was measured that graphite has a plasmon mode, which is completely flat. As you see, these are experimental dots made 20 years ago, and very flat and in the range of tens of millielectron volts. So exactly the same frequency as water. And so meaning that this overlaps very strongly with water. So meaning that actually it happens that graphite behaves a bit like an harmonic oscillator, which is in phase with the water as an harmonic oscillator. So you expect a lot of crosstalks, a lot of dissipation. And so, oops, and so at the end of the day, what you have is that in terms of friction of water and graphene is basically zero, because you have no quantum crosstalk. But for graphite, because of this strange plasmon, you have a huge friction, and exactly in the range of what is measured actually on friction. So this explains that actually the friction of graphite is much strong, orders of magnitude stronger than what you would expect on graphene. And now if you go to carbon nanotubes, actually it happens that when you when you start to bend the graphite layers, so the multi-wall graphite as shown on these layers, it happens that you cannot get any more this plasmon in these layers of graphite. And so basically, again, to make a long story short, it happens that when you start bending the graphite to make multi-wall carbon nanotubes, all the layers will be misaligned. So at the end of the day, water only talks to the first layer, and this comes back to graphene. So that's why basically you have high friction, so low slip lengths at high radius, and low friction, so high slip lengths at small radius. And okay, so that's a I mean, that's in some sense an interpolation between the various results that I showed here. So that was interesting because you see you start to see that water can talk to the excitation inside the solid. So the solid are not, fixed. They can move inside, and this motion inside can dissipate energy also. And so we wanted to go beyond, and so okay, so that was experiments, and we did some theory, and then we wanted to come back to experiments. And okay, so that was the work of Mathieu Lisée and Baptiste did some theory on that. And what we wanted to do is say, okay, if we have this perspective of excitation, instead of moving the excitation of the solid, which can be hard, but okay, that's what we do now, but that's quite hard, why not taking a fluid where we can move the excitations? And actually, a simple fluid which can do that is glycerol. And glycerol is it's a glass maker in some sense, and glycerol has a viscosity which depends very strongly on the temperature. And glycerol actually its viscosity increased by orders of magnitude when you move by a few tenths of degrees. But if you look at, so that was that's a viscosity that you can obtain in a rheometer. But actually, when you put when you look at the spectra, so just I showed you previously the dielectric spectra, so that's the same. Actually, it happens that glycerol also has a kind of Debye peak, which depends very strongly on the temperature. So actually, when you move the temperature, let's say by a few tenths of degrees, you see you have a characteristic frequency inside glycerol, which moves very strongly as a function of temperature. So that's a great opportunity, you see, because we want to move to compare the two oscillators. So you can move in some sense one oscillator, the frequency of one oscillator, as compared to the other one. So there, okay, that's another class of the experiments that was done during the PhD of Mathieu. And what we use there is tuning fork experiments. So tuning fork, it's an interesting AFM in some sense, atomic force microscope, where you have an oscillation of the fork. So it's a oscillating fork. So here it's a fork that you have in your watch. So it's a typically 32 kilohertz fork, and it moves. You excite it, but then of course, if you have something in between the, let's say, a tip and the surface, of course, it's as if you have an oscillator coupled to another oscillator, so it will move the resonance frequency of the oscillator. So by measuring the resonance frequency, you can deduce what are the elastic properties of the fluid between the tip and the surface. Then, also, of course, if you have something which is very dissipative, like chewing gum or something like that, of course, this will slow down the tip, and the quality factor of the oscillator, the tuning quartz oscillator, will get down. And from this decrease of the quality factor, you can infer the dissipation. And so this, I mean, this type of experiment is a very precise experiment of the properties of confined systems. And so, so it's really now, in some sense, it's really rheology in this case, because you have a dashpot model in between the tip here, which is, I mean, modeled by a sphere, and the surface. And from this dashpot model, you can describe the surface friction. And so a typical way to do that, and it's very close to measurement done using, for example, surface force apparatus. From this such measurement, you measure the dissipation versus the distance, versus the confinement. And what you get actually is actually from this measurement, you can infer the slip length. And this was because the slip length, in some sense, it's as if you shift the boundary condition inside the solids. So you have a slight shift of the here you see you have a slight shift of the inverse dissipation, so which is here versus the distance. So just it's really a measurement of the frictions properties here that you can do with this system. And so Mathieu did that for many systems with various temperatures from 30 degrees down to 2 degrees, and from this response, so the dissipative part of the mechanical response, you can infer the slip lengths. And so here, these are the raw data, and the solid lines are the fit using these predictions from the Reynolds formula. And you have a very good estimate. So you have the slip length versus temperature. And what is interesting, so I forgot to say that the surface here, actually we chose mica to start with. And mica, of course, it's a non-conducting system, so you will have no plasmon, but still, okay, that's a system which we could study. So this is a slip length versus temperature. First, okay, so we found the slip length is very large for low temperature, for you see glycerol on mica, and the slip length decrease with temperature. But more interesting, actually, is the friction coefficient. So really the friction of glycerol on mica. So actually we found that the friction coefficient had, you see, this kind of non-monotonous behavior. So it first decreased with temperature and increased again. And that's very weird because it's a non-Arrhenius behavior. It's, I mean, an Arrhenius would decay all the time versus temperature. And actually, if you remember, actually there is a strong connection between the characteristic frequency of glycerol and temperature. So you can replot this friction with the relaxation rate. So you see that there is something very strange in this system, that the friction versus the characteristic time of the liquid is a non-monotonous function. Okay, so okay, maybe I will skip this part because I was a bit too long, I think. So what I wanted to show you in this system is that you can understand again this strange dissipation by the fact that the glycerol molecule, so the oscillation in the glycerol molecule, which has a specific frequency, actually can here correlate or be in resonance with the vibrational modes of mica. And vibrational mode means phonons. And actually, so instead of plasmon, here it's a phonon. So again, an excitation inside the solid. And when you, okay, I make a long story short for the model, but actually you can really fit the data, or at least show that it's a non-monotonous behavior with the friction, which is first decaying with the characteristic time of the liquid, but then increase again. And in some sense, it increases again because you have more and more modes of phonons, and you can dissipate much more strongly. And that's a very weird result. Okay, so I was a bit long on that, but what I really wanted to emphasize is that here, instead of looking at the continuum model of fluids, we think in terms of an excitation. So let's say water, we not only consider its viscosity, but all the modes inside. And these modes can correlate to the surface. And this really gives us a lot of, okay, I will skip this part. This gives us a lot of possibilities, I mean, to revisit friction with materials which can respond to the excitation that you have in fluids. And actually, you can even go beyond because, for example, in this system, we can think that if you have a flow, you can excite some excitation inside the solid, but then this excitation can induce a flow across the solid. So you have a kind of a flow tunneling effect, which is, as you know, the tunnel effect is a quantum effect. Here you have the flow tunneling, but you have the tunneling effect, but for momentum. That's a momentum inside the liquid can go across the wall if you account for the excitation inside the wall. And so we did some prediction about that and some simulations, and indeed it works. So you can cross solid walls here. Okay, let me skip that. I don't want to enter. So that's what I wanted to say. And you see that that's really, we are really at the beginning of exploring all that and trying to understand all these two couples, and we hope that it will tell us a few things. So maybe in the last 5 to 7 minutes, I wanted to discuss a slightly different point. Is that okay? Okay, we have as scientists, we have a lot of fun, going into fundamental science and exploring new things and etc. So get into the lab, but it happens that okay, first I'm very emotional about the climate crisis. So let's say, what can we do about can we apply all that we know in the lab to something that can be useful for the society in general? So that's sometimes a bit ambitious, but okay, can we say things like that? And so that was the topics which of high interest to me, and I felt a bit committed as a scientist to propose things, at least to try. And so there, this is connected to what is called the water energy nexus. So water energy is basically that you need a lot of water for energy. Just think for how much of water you need to cool nuclear plants or to cool the artificial intelligence power systems. Also, or for hydrogen, for example. And you need also a lot of energy for water. For example, if you want to desalinate, you need a lot of energy. And so, and the huge difficulty when you are in your lab, so let's say, okay, we see all these fancy effects. Let's say, can we use one of these fancy effects to have a new method for desalination, for example? And then you have a huge problem, because of course you see a lot of groundbreaking, let's say, effects at small scales. So let's say super fast flows of water in carbon nanotubes. But if you want to apply this for desalination, you will need to have, let's say, 1 million square meter of membrane, basically. So that's, for example, that's a desalination plant from in Israel, Ashkelon, which produce a few thousand cubic meter per day. All this is basically 40 square meter of membrane, all this vessel here. And you see you have thousands of it. And so you see, you have these huge difficulties that any effect that you see as a nanoscales should be scaled up to the very large scale. And that's a technology killer. And that's what we have to solve whenever you want to go out of the lab. And so I just would like to show you one example of basically, again, an adventure that I was involved in. Actually, I've been much interested in what is called osmotic energy. So osmotic energy is, in some sense, what I say, the dream of harvesting entropy. The fact that if you, between river water and seawater, of course, you have the entropy of mixing of the salts. And this is small. This is basically 1 kilowatt hour per cubic meter. It's orders of magnitude smaller than oil, of course. But you have lots of flux. So, for example, if you take the Amazon, I mean, I'm cheating because that's the highest flux in the world. Amazon is 200 cubic meter per second. So if you multiply this flux by this energy, you have 1 terawatt. So meaning that the Amazon is wasting 1 terawatt. So it's 1,000 nuclear plant. So of course the Atlantic is so huge that it does not boil, but you see it's a huge power. And if you think, I just mentioned that to say that, of course, we cannot harvest 1 terawatt for the Amazon, but at least it tells you that it's a huge power. And typically, one considers that around the world, we have more than 1,000 gigawatts, which could be harvested. So it's the equivalent of 1,000 nuclear reactor. So it's not at all small. And the huge problem is that there were some technologies, which I will not discuss, which were extremely inefficient to harvest this energy. And so it happens that the first experiment that we did with nanotubes, actually we showed with boron nitride nanotubes that if we put a difference of salinity between the two reservoirs, we had a huge ionic current moving across the nanotube. And that was really unexpected. First, because, of course, to harvest, it's an osmotic power, so you need osmosis. And there, we didn't expect osmosis because the nanotube was quite big, so it's not semi-permeable or whatever. But actually, it happens that it's a weird osmosis, which is called diffusio osmosis. It's an osmosis on the surface. which happens can be extremely efficient if the material is very charged. And it happens by luck, so it's serendipity, that the boron nitride materials, we measure that it was extremely charged on its surface. So we had these experiments and we think, oh, we should do, okay, we did a patent, but how to make to go from the single nanotubes to a real membrane to a pilot plant, an industrial plant. And of course, you cannot use thousands of nanotubes. It would cost $1 million per square meter of membrane. So that's completely insane. But the key aspect of it is that it had a new blueprint in the sense that we knew that we could use this diffuse osmosis, and we were looking for different materials as compared to the other technologies, which were the previous technologies. And so it opens a range of possibilities. And okay, so I will skip that. And the way to do this screening, actually, the way I did it is that honestly, I realized that it's very difficult to do that in a lab because you have to transform. Okay, we are curiosity driven in the lab, and there you have to have a mission to develop that. So, for example, so that's why we with some investor we co-founded a startup which is called Switch Energy. And this startup really, I mean, it was created in 2015, and for 7 years, basically, it was just search of materials, search of new geometries, etc. But you see that starting from the nanotubes, that's typically the scales where they are now. So you see that's an osmotic reactor, and the target of the startup, the mission, was to say, can we do on industrial scale, so let's say tens of square meter, a conversion of energy above 5 watts per square meter, because it's basically an break even, let's say. If you are able to go above 5 watts per square meter, you can make it industrial. And it happens that they bypass this break even just before the summer on a 20 square meter membrane. So meaning that now they have a small module, osmotic module, which is basically the Lego brick, as I was saying here. And now you just have to pile up the Lego bricks and extend. So that's what they are doing now. So for example, that they are doing now a pilot plant. So that's the tubing. Okay, they are quite secretive. So I'll just show you a very simple image of it. But now they are doing a pilot plant, incorporating all these modules, which are now parallelizing and producing osmotic energy. And so this is a story I wanted to say that, okay, I think startups, and I had a few experience with that, they are extremely efficient for upscaling because they have a mission, a very specific mission, and you can connect fundamental science and really basic science to something which can be useful. So here I showed osmotic energy. Actually, we have been creating another startup to do additive manufacturing, and now we just launched a new startup about unconventional desalination using electric fields. And I just put also the money raised because, okay, it's not to show off, it's just to say these startups, they are able to attract money and put all this money on a mission, which is extremely well defined and put a lot of people. And that's something we cannot do in the labs. So, okay, so that was my experience. And with this, I thank you for your attention. And just before I close, that we have two positions in my group, in my team. One on CNRS, but the deadline is very short. And later in spring, there will be a maître de conférence or lecturer position in my team. So if anyone is interested to do nanofluidics and to have all these projects, I will be just contact me, and I'm looking for enthusiastic people to do that. And with this, I thank you a lot for your attention. And sorry, I've been a bit long, but I hope it's okay. Bye.
Thank you so much, Lydéric. And you've not been long. It's just perfect like this. Wow, it's a lot of information to process. And well, questions. Let's just go ahead with questions. Do we have questions from the attendees, from the public?
Maybe I could ask like one question because I was wondering for the experiments first. Like whenever you do those kind of experiments, I guess it's super challenging with some noises, with like thermal noises and so on. How do you decorrelate those noises from the measurements that you want to do? And also like how do you decorrelate the surface driven sleep and so on from the bulk mechanisms and so on? Because I
Yeah,
guess it's super challenging.
yeah, so I actually, okay, so first about the noise, indeed, I mean, okay, the great thing is that measuring electric currents, so ionic currents,
Yeah.
it happens that it's quite easy and you have an incredible sensitivity. You
Okay.
can go, I mean, up to femtoamperes, so a few tens femtoamperes. So, and that's really thanks to the great job of people in biology and physiology where they develop this system. So meaning that you actually measuring a current inside a single nanotubes, you get out of the noise because of that. And
Okay.
that's what for example, I was showing one example initially, I think, and I can't remember where I showed it, but
Um,
uh, yes, maybe yes. For example, here
this one. Yeah.
you see the noise is extremely small.
Oh yeah.
Yeah, and so that's a beautiful measurement that was done by Alice Marcotte,
Mm,
and you see we measure picoamperes here, which is very large
yeah.
actually. Because here it was a single nanotube, but you see the noise is really within the range of 100 femtoamperes, I guess, in these measurements. So first, of course, then for measuring the flow, it's much more difficult measuring the
Mm,
flow.
okay.
So that's why in these experiments I was showing you here and
This.
here.
Yeah.
Yeah. So for example, that's the permeability, which I forgot to show. Okay, measuring the permeability, honestly, it's for example, that's why it's not possible to measure below 15 nanometer radius system
Mm,
with this technique here, because
okay.
here you are within the noise, below that. So in some sense, here, in particular for the carbon nanotubes, what is great is that the slippage increased when you go to
Mm,
smaller tubes. So meaning you can still measure something, and
okay.
that's the luck. But you, for example, for the boron nitride nanotube where you have no slippage, it's impossible. For example, this open circle is just a
Yeah.
failure.
Okay.
It's a no.
Yeah, I see. I see. I guess it was a bit like this. So yeah, I understand. Okay, thank you. Yeah, we have
I have
questions.
absolutely no experience in manufacturing nanotubes. How hard it is.
So, I mean, fabricating the nanotube actually, now you can really buy it on the internet
Wow.
because nanotubes now are really, I mean, people are putting this in as reinforcement for elastic response, usually, for example. So it's very standard to fabricate nanotubes, and you can do various techniques. So, for example, you can do chemical vapor deposition. So you grow nanotubes with a catalyst on the surface, for example. But and then you can do to have very beautiful one. You use electric arc, so you put a very high voltage between the two. So but to have beautiful ones. So lately we are working with people from here, the lab, but also people from Montpellier, where they are able to do double wall nanotubes, which are 100 micron length and a few nanometer, 1 or 2 nanometers in diameter. So, and now, I mean, that's very know-how, but okay, to reach these incredible nanotubes, okay, you need a lot of work, but to have basic nanotubes, you can even buy them on internet. And
Okay.
for graphene, it's different. So graphene, it's a Scotch tape technique that was
Mm,
developed for mica, but that GAIM used for the the graphene measurements. Yeah.
I
yeah.
see that people in the chat are thanking you for the amazing talk, and they're saying that it's a Christmas gift in advance.
Thank you. Thanks a lot.
That's
I
true. That's
really
true.
appreciate it.
Let's see if we have other questions, other scientific questions, because otherwise I do have another question, but it's more related to the startups. Elizabeth, please.
Yes, thank you very much, Lydéric, for this amazing talk.
Thank you very
I
much.
have a very general question. I never understood why the friction is proportional to the velocity.
The friction force, you mean? Yeah.
Yeah, the friction force.
Yeah, because it's basically linear response. Because here water is gentle, so it's not a complex fluid. Okay, it's complex by other aspects, but it's not a complex fluid, so it has a and so the fact that the force is proportional to the surface velocity, it's a bit like what happens in solid, not solid on solid friction, but how to say that's I mean, at zero velocity, you have zero force here because you have it's a thermal systems, but then it's only a proportionality factor, I would say. I don't know if I'm very clear about that, but
But not totally. My question is also why you don't. Why is it impossible to think that when you decrease the dimension,
mhm.
you are going to have a solid friction?
Ah,
So, for instance,
okay. So then the question is, could the water transform into a solid phase then if you have solid friction?
yeah, something like that. Yes.
Yeah, and actually, I would say so. As I was showing, indeed, for water in very strong confinement, it's nearly it could be crystal-like, and that was I was showing in this experiment by Strano, for example. They say that okay, you have crystallization maybe of water. Now, this occurs in the smallest nanotubes that can exist, and I don't think that anyone has measured the friction inside this. In any case, in our nanotubes, which are a bit bigger, we never saw any signature of solid friction, let's say. So
Okay.
everything is proportional. So you see, for example, the way we measure it is that we can infer it because, for example, the flux of water is proportional to the pressure drop, or the flux, the ionic current is proportional to the pressure drop. So then you have linearity, meaning that you have no solid friction. But it could happen. I agree with you if you are really in this, if the water has another phase, or for example, if you have a for example, if you put glycerol at minus 70 degrees, for sure it will become a solid and it should have a solid friction. But we were not able to measure that.
Okay. Thank you.
Thank you for the question. And well, I don't see any more questions coming. I'm just gonna ask a question that it's not scientific at all, because we like to talk about also what to do after a PhD with the students that come to these webinars. And startups are usually also a very good choice for, and as you said, it's a very mission-driven environment, but still very close to academic research. And one very I mean, it's a very basic question based on curiosity. How long does it take? And I guess it's also country based, the answer. How long did it take for you to start those startups?
So
And also how hard would it be for somebody young?
yeah,
Younger, I should say. Sorry for that.
actually, okay, okay. So Switch Energy was created 10 years ago, let's say. So you see. Actually, a good example maybe is that the startup about desalination that we are just currently creating, and okay, and they are all very young people. There are one postdoc from the team, one engineer, and two engineers, let's say, and they are 24, 25, and 30 years old. So the meaning that's really the beginning of the career. So then the way it usually I develop these startups is that in the lab in my team I have what I call the spin in. So by spin in is for me it's a bit of a joke about spin off. So spin in meaning it's a small team of people, so engineers in the lab, and where their goal is to actually develop proof of concept. So you see, or do patents, discuss with industry people. So they have no goal about no objective in terms of papers, but objective rather in terms of intellectual property, and etc. etc. And there, for example, the two last startups, they were creating along these lines, so that they stayed within the lab for 2 to 3 years. We try to develop together the technology, starting from ideas from these experiments, fundamental experiments, and develop some larger scale proof of concept. And after 2 years, then okay, you have patents. Okay, you say, okay, now I'm ready to I have a proof of concept, so then I can go to investors. So this takes basically 2 years actually. And now they will get out of the lab, so next January, so in a few days, and there they will get money from investors and develop their own, roadmap, and which is really mission oriented, as I was saying. So I don't know if it answers your question, Michel, but I would say it takes 2 to 3 years actually to go to. The difficult part is that indeed we all do, we are what we call deep tech. So, okay, we put the hands in the mud. So it's not IT startups, where you just make a code and just, I say, so it's quite costly to fabricate things and very tough because, for example, membranes are a bit of a nightmare. And so this means that it's very important to have a close connection to the lab for all this transition period. And then after, okay, then they grow and etc.
Yes, it definitely answers my questions. And this pin-in idea I never heard about, and sounds very cool.
Thank you.
Okay. Well, if we have no more questions, I guess we can stop the recording here.
Okay.
And
thanks a lot for the invitation again.
And
thank you. Well, then I'm gonna stop the recording. Bye, YouTube.